Welcome back to Trigonometry. We're in week 3. Today what we're going to do is we're going to work on jumping from our unit circle, which we've been working with recently, towards what we call periodic modeling. So to start things off, let's take a look at what are the learning objectives for this asynchronous assignment. So today what we're going to do is we're going to be, first of all, taking a little bit of bringing us back up to speed on what we've been doing. We're going to use what we call reference triangles in order to solve problems which involve trigonometry outside of just the context of the unit circle. Additionally, what we're going to do is we're going to develop an understanding of what periodic behavior is. We're going to connect the unit circle with periodic models which, model these periodic behavior that we're discussing. And we're going to eventually derive a model of the sine function. To start things off, we have two different problems which are going to each require us to use right triangle trigonometry in ways that are beyond the unit circle. So this first problem, we have a 10-foot ladder and it is leaning at an angle of 71 degrees against a building, and it reaches towards the rooftop of that building. We're curious, how high will the ladder reach on the building? To start things with this, it'll be useful if we pull up our whiteboard and we draw a diagram. So this is a pretty standard trigonometry problem, which you might have actually solved in your geometry class in the past. So to start things off in our diagram, let's go ahead and draw ourselves a little house with a rooftop. And we have a ladder which is leaning against the side of this house. So I have a ladder drawn right here. We knew that the ladder was 10 feet long. Now that's going to be actually the length of this ladder right here. So that's going to be 10 feet right here. And it leans at an angle of 71 degrees. So what that's going to be, guys, is it's going to be we call this the angle of elevation. All right, it's the angle which your object is elevated above the ground. So this is going to be 71 degrees. Notice that it creates a right triangle against the side of the building. So our question is, how high will the ladder reach? This seems like we're just trying to calculate height here. And if you can see, in our diagram, what we've got here is a right triangle. We know the angle. We know the hypotenuse, and we are looking for the opposite side. So we want to relate opposite with hypotenuse. We have a function in our trigonometric tool set which does this. We actually have two functions. The sine function, which is equal to the opposite divided by the hypotenuse. Keep in mind that's sine of the angle, right? It's equal to the opposite side from that angle. In this case, it'd be h. We also have another one which is cosecant of theta, and that's the reciprocal of sine. It's equal to the hypotenuse divided by the opposite. Now, I could actually use either one of these trig functions to evaluate this. I'm, however, going to use the sine function, and the reason why I'm going to do that is because I know the hypotenuse. The hypotenuse is going to be 10 feet. The opposite side is h, and I know my angle, which is 71. The reason why this is useful to set up this sine function instead of the cosecant is because literally just it's going to be easier to solve. Notice that in order to get h on its own, all I have to do is multiply both sides by 10, right? Whereas if I was working with cosecant, my variable h would be in the denominator. And as we saw previously when we worked with rational equations, having variables in your denominator is never the optimal move, right? It's always just a little bit more annoying. So one of the cool things in math is that because there's oftentimes multiple ways you can set up a problem, there's oftentimes a way that's easier than the other. So by using a little bit of consideration, I can make my life a little bit easier. So I multiplied both sides by 10. And so I get that the height is equal to 10 times the sine of 71. That's going to be something that I can evaluate with my calculator. Unless we have some of our angles which are on the unit circle, such as, for example, 0 degrees, 30 degrees, 45 degrees, so on. Unless I have some of those unit circle angles, I'm going to use a calculator to evaluate this. So if I pull this up on my calculator real quick, I would get 9.51. So the height is equal to 9.51. And now that's not my final answer, right? Because remember, we're working in a context. And when we're working in a context such as feet, you want to include those units. So the height that the ladder reaches is 9.51 feet. Right triangle trigonometry is useful for evaluating such measurements like this and looking at how tall is a building, how high is something, how big is a distance, and so on. That's the really simple applications of trigonometry, which we've seen in geometry before. Now let's go ahead and take a look at that second problem. So this second problem is a little bit odd because I've been given the evaluation of a trig function for some unknown angle theta, right? I do not know what this angle theta is. In fact, I'm actually never going to know in this problem. If I know what tangent is, then I can solve for all the other trigonometric evaluations without ever finding that angle theta. So the way that I'm going to do this is I'm going to draw what we call a reference triangle. Drawing a reference triangle is essentially very similar to drawing a model, like we did in the last problem. However, what we're going to do is this reference triangle is going to be actually on the xy axis, because this is something that we're just kind of pretty used to. If the tangent of this angle is equal to the square root of 2, there's actually two different triangles that this could be. There's actually two different angles that this could be. If you kind of have started to observe the patterns of the unit circle, the coordinates tend to repeat themselves. And in fact, they don't just repeat themselves in the sense that, oh, we have the positive and the negative positive version of each other. They repeat it themselves in the sense that, like, for example, the tangent of theta could be the square root of 2 if I had a triangle here where the angle's theta, and tangent, if we remember, is the opposite over the adjacent. So the opposite side divided by the adjacent should be square root 2. To do this, I could just make the opposite side square root 2 and the adjacent side 1, right? In this case, the tangent of this angle would be square root 2 divided by 1, which is square root 2. The other way that this could have shown up, actually, is in a triangle that's in the third quadrant, where this side length here on the opposite would be negative square root 2, and the adjacent would be negative 1. And then this would be theta, this whole angle there. So actually, there's two different ways in which this could occur. So this problem should have given us a quadrant that the angle was in. So that's my bad. Let's, for the sake of this problem, let's say that we knew that the angle theta was less than or equal to 3 pi over 2. And it was greater than or equal to pi. Which quadrant would that place me in? It would place me in the third quadrant, because at this point here is where pi is for the angle, and at this here is where 3 pi over 2 is, right? So I'm going to go ahead and erase my first quadrant triangle here. I'll remember in the future to give you guys which angle we are working with. Or not which angle, but which quadrant we're working in. And the reason why this matters, by the way, guys, is because there'd be a difference in my sine. Even though the tangents are the same for those two triangles, the sine, the cosine, and so on would be different because of this different xy coordinates being positive versus negative. So now that we have this reference triangle that we've drawn, it's a right triangle, and it fits our description that the tangent of the angle is square root 2, we want to evaluate all these other ones: sine, cosine, secant, cosecant, cotangent. In order to do that, all we need to do is know what the opposite, the adjacent, and the hypotenuse are. We're already 2/3 of the way there, right? We've got the opposite and we know the adjacent. So let's calculate the hypotenuse. To do so, we're going to use Pythagorean theorem. A squared, so negative 1 squared, plus b squared, so that's negative square root 2, squared will equal the hypotenuse squared, c squared. Negative 1 squared is 1. Negative square root 2 squared is going to be positive 2. So c squared will be equal to 3, making this hypotenuse here square root of 3. All right. So now that we know our 3 side lengths for this triangle, we can begin actually evaluating those trig functions. And it'll be pretty quick for us, right? So the sine of theta would be the opposite, which is negative square root 2, over the hypotenuse, which is the square root of 3. Now, I'm going to want to actually, remember, rationalize my denominator here. So what I need to do is I need to take this and multiply the top and bottom by square root 3. And that gives me that the sine of theta here is negative square root 2 times square root 3 is square root of 6. We've discussed this in class, but remember, when you have two square roots multiply each other, their insides will multiply into a single square root. And then square root of 3 times square root of 3 is 3. So negative square root of 6 over 3 is the sine of this angle. What about cosine? Cosine of the angle is equal to the adjacent over the hypotenuse, negative 1 divided by the square root of 3. So once again, I need to rationalize my denominator here. So I end up with root 3 divided by root 3, multiplying it. And so my cosine is equal to negative 1 times the square root of 3 is negative square root of 3 over root 3 times root 3, which is 3. So that's my sine and my cosine. Now what I think I'm going to do is I'm going to leave evaluating the secant, cosecant, and cotangent up to you guys in our asynchronous notes check. All right. So you guys have that to look forward to. Now let's go ahead and move on to what this video is truly about, the periodic behavior. To start things off, I wanted to define periodic behavior. So periodic behavior describes any interaction or mechanism which consistently repeats itself in regular intervals. So if you see here, I have a Newton's cradle displayed. And what happens is as the ball gets knocked to either side, it has the force of gravity swing it back to knock the other side back again. And this motion will repeat itself over and over and over. And it's going to keep going at regular intervals. This is periodic behavior. What we're going to do is we're going to go ahead and expand our understanding of the unit circle to encompass the modeling of periodic behavior. So if you guys see here, I have the unit circle displayed. And what I want to show you guys is this Ferris wheel. The unit circle and the Ferris wheel are extremely similar. In fact, you may notice that this Ferris wheel has spokes at all of the exact points and angles that the unit circle does. Maybe not the exact, but close enough. Something that you guys should observe here is that they are comparable to each other because they both complete a full revolution periodically. The unit circle goes around in its angle every 360 degrees or every 2 pi radians. Similarly, a Ferris wheel, as it goes around and around and around, will continue to repeat itself however frequent that may be. For example, a Ferris wheel could have a cycle of 2 minutes. Another thing that's comparable between the two of them is that they both have consistent maximum and minimum values. See how the unit circle, its maximum value up here is at y equals 1, and its minimum value here is at y equals negative 1. Similarly, the Ferris wheel will go up to a peak, and that's where you get the best view if you're riding the Ferris wheel. And it goes down to the bottom, which is usually where people get on the Ferris wheel. So when we're looking at the behavior of this Ferris wheel, what happens is we get on at, say, the bottom of the Ferris wheel, and we go around the circle, and we go up and up and up and up until we reach the top, where we can see that beautiful view, and we say, oh, wow, what a beautiful view. And then it keeps going, and we go down, 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 down. Maybe it goes through a couple cycles, but that's essentially the point of the Ferris wheel. even though the Ferris wheel functions in 2 dimensions, right? As I go around, I do still go to the right, right? And as I go around, I go to the left. I don't really care about that, do I? What I truly care about is that height. In a similar vein, I could focus on just the height around my unit circle. That's just those y coordinates, right? As I go around the unit circle, I could exclusively look at the y values, and that would be a really useful way for me to compare the unit circle with the height as I go around the Ferris wheel. Luckily for us, we actually just so happen to have a function which models the height around the unit circle. Remember, guys, the height as I go around the unit circle can be measured by the sine function. We've seen before that the sine of any angle around the unit circle is equal to the y coordinate, correct? So what can happen is I might be able to use this sine function to model heights around a circle. In fact, because the sine function models the height of the unit circle, we can use the sine function itself to model periodic behavior in a single dimension, such as that height on the Ferris wheel. This means it will prove very useful for us to understand the sine function itself on a greater level for our future modeling purposes. So what we're going to do today, y'all, is we are going to develop that sine function model such that we can eventually model all sorts of periodic behavior. Things like the Ferris wheel's height, the tides of the ocean, the movement of the planets in the solar system. There's so many things that trigonometry can be used for once we start looking at trigonometric and models involving periodic behavior. So what we're going to do in order to develop a model of the sine function is we're going to actually just evaluate a bunch of different angles of sine around the unit circle. So if I wanted to find a bunch of angles around the unit circle, it might be useful for us to just kind of do every half pi, for example. So let's go ahead, and what we're going to do is we have our unit circle, and we are going to essentially evaluate all these coordinates of what happens as the input of my function. Remember, guys, the angle theta is the input of the trig function sine. So what I'm going to do is I'm going to find when theta is 0, right? What is sine on the unit circle? Well, sine is the y coordinate, remember? The y coordinate at 0 radian is y equals 0. So I have 0 here, and what I'm going to do is I'm going to plot 0, 0 on my axes. So let's keep going with this. What about pi over 2? Well, pi over 2 is going to be 1, right? Because here at pi over 2, the y coordinate is 1. So let me go ahead and plot that on my graph. So at pi over 2, my y value is 1. We can keep going with this, y'all. At pi, at the angle pi, the y coordinate is 0. So I place a dot there at pi comma 0. At 3 pi over 2, my y coordinate is negative 1. So I'm going to place a dot over here at negative 1. And then at 2 pi is where I've done a full circle, right, guys? So actually 2 pi is going to be the same thing as 0. So what's going to happen is it's going to repeat itself. I'm going to be back to y equals 0 for 2 pi. Similarly, 5 pi over 2, right? That's just another half pi past 2 pi, right? Because 2 pi would be 4 pi over 2. So if I go another half pi around, I'm at y equals 1, right? And if y is equal to 1 at 5 over 2, then I plot that on my graph. 3 pi is one full loop around, and then another pi, and that is at y equals 0, right? So here's y equals 0, and you can see at 3 pi, I've got a point here at 0. 7 pi over 2, that is where I've gone one full loop, right? And then I need to do another 3 halves, so down here. My y coordinate would be negative 1. And so my plot goes there at negative 1. And finally, we have 4 pi. 4 pi would be actually 2 full loops, which puts me at y equals 0. And there's my dot. Check that out, y'all. So here, what I've done is I've essentially created a table of values for the sine function. I've plotted them on a graph where my x-axis is scaled by fractions of pi since I'm working in radian. And my y-axis is showing the values of sine at those different angles. Let's go ahead and connect all these dots. Now, I'm not going to connect these dots in straight line because if you can see, the height of my function is kind of curvy. It curves around. It doesn't actually go directly from 0 to 1 in a straight line. It's not linear, right? It curves. So what I'm going to do is I'm going to use curved lines in order to connect all these dots. So here I have done so. This is the sine function, what you see here. Now what I wanted to do was kind of point out a couple of the features of this sine function for you guys, okay? So remember, this is sine of theta. So something to observe here in sine of theta, we call the amplitude is how far up it goes, right? And how far down it goes. We don't concern ourselves with how far up and down it is because they're the same thing. Notice however far up it goes is how far down it goes. And what you might notice is that it's 1 unit. Why is it 1 unit? Well, that's because if we look at our unit circle, remember guys, the radius of the unit circle was 1. So our sine function has a amplitude of 1 unit. Something else to observe, y'all. Notice that the period of repetition, right? Yep, my little thing's blocking it. The period of repetition for this function is 2 pi. Essentially, after I've gone for 2 pi on my inputs, I reach where I had started, and it begins again. Notice how this first half of the function looks the exact same as this second half of the function. That's exactly why sine functions and cosine functions and so on will be able to be used to model periodic behavior because they themselves are periodic. And here you can see that I've actually included a animation to show us the sine function essentially being created. So as my radius circles around the unit circle, you can see that the heights of the unit circle and this function here are essentially measuring each other, right? They're the same measurement. And this graph here I've shown in terms of degrees so that we can kind of get an idea of how it looks for both of them. It looks the exact same. All that's happened is I've changed the scaling of my x-axis. Now, typically in our class, we're going to work in radian. So we won't actually worry too much about this graph with degrees, but I really liked this animation and I thought that it kind of helps us see what the sine function looks like as it's being turned into the graph. So that's about it for today's lesson. So let's go ahead and recap what we did. So we used at the beginning reference triangles in order to solve various problems which involve trigonometry outside of the unit circle. Then what we did was we worked a little bit to develop our understanding of what periodic behavior was with that Ferris wheel and with the Newton's cradle. We connected the unit circle with periodic models by comparing the similarities of the unit circle and measuring height around the unit circle with measuring the height of the Ferris wheel. And finally, we derived a model for the sine function. We actually created the graph of sine by evaluating it at different angles. So to finish up today's video, I just wanted to go ahead and give you guys a little sneak peek of what is to come. So what we're going to do in the future of our class is we are going to take the idea of our sine function model and we're going to try to work it in order to match the idea of our Ferris wheel and the height of the Ferris wheel as it goes around. So that's something you can look forward to next time.